here we go. We are going to continue with section 3.3. This is a long section, but it has a lot of important stuff in it. So we are going to just spend the time that we need on it. Section 3.3 continued. We're going to talk about a subject called concavity. And this is a subject that you've probably seen a bit of before, at least. A graph is what is called concave up if it's shaped like this. It sort of curves up more and more as we go from left to right. We would call this concave up, like a cup. And then a graph is called concave down if it is curved like this. So it tells us about the shape of the graph. We would say that this graph is concave down. Okay. Let's see here. Maybe let's draw some lines tangent to these graphs. This one on the left. I'm going to draw a tangent line there. So it has a negative slope. Move a little further to the right. Tangent line there. It still has a negative slope, but it's less negative because it's less steeply sloped. Move a little further to the right. It's still slightly negative sloped, but barely. It's a little bit larger of a slope. And then if I move further to the right, it looks like the slope becomes positive. So let's see, what might we say about that? We might say that as x increases, so as I move from left to right on this graph, I might say that as x increases, the slopes of the line tangent to the graph are increasing. The slopes of the lines that are tangent to the graph, tangent to, we'll call this the graph of f, are increasing. Let's see, what might we say about that? If the slopes of the lines tangent to the graph are increasing, this means that the derivative, which represents the slopes of the tangent lines, f prime of x, is increasing. Not negative, but it is increasing. Well, that means that the derivative of this function here, which would be the second derivative of the function f, is positive. So this means the second derivative, f prime prime of x, is positive in this location. So it looks to me like the second derivative, which we haven't really used much at this point except to find the acceleration of a position function. We're now going to bring into play and use it to find, well, what's the shape of a graph over an interval? I can state something very similar about a concave down shaped portion of the graph. We might see here that if I were to draw lines tangent to the graph of f, then tangent line will be positive here. As I move further to the right, it's still positive. The slope is still positive, but it would be less positive. I move further to the right, that slope is 0. Further to the right, the slope becomes negative. So it looks like the slopes of the lines tangent to the graph are decreasing. So I might say that as x increases, as it increases, the slopes of the lines tangent to the graph are decreasing. The slopes of the lines tangent to the graph of f are decreasing. So that means that the derivative f prime of x is decreasing as we move from left to right. Therefore, the second derivative, which is the derivative of the first derivative, is negative. So I use the first derivative to tell me whether a graph is increasing or decreasing. I use the second derivative to tell me about the shape of the graph. Is it concave up or is it concave down? Okay. So that is what happens when the second derivative is positive. This is what happens when the second derivative is negative. Graph is concave up when the second derivative is positive, concave down when second derivative is negative. What about when the second derivative is equal to 0? Let's talk about that. Let's see here. What if I were to draw this graph? Here is a graph of f. And let's have it look something like this. Let me actually redo that. Get a little bit less steeply sloped. Okay. So there's my graph. It looks like to me that the graph here is certainly concave down. So that means that the derivative, f prime, in this location, f prime prime, excuse me, the second derivative, since this graph is concave down, the derivative will be negative there. And then over here, in this portion of the graph is concave up. That tells me something about the first or the second derivative in this location. Here, I know that the second derivative is positive because the graph is concave up. Okay? At some location in between here and here, that graph has to change from being concave down to concave up. Looks like that location is maybe right here. So it looks like at this point, the graph changes from being downwardly curved to upwardly curved. This is the location, as you can probably imagine, where that second derivative, f prime prime of x, is equal to 0. And just like I have specific names for locations where the first derivative is equal to 0, I have a special name for this location where the concavity changes. I would call it an inflection point. An inflection point. Inflection point is a location. It's a point where the concavity changes. Where the concavity of a function changes. And it will always be the case if a particular graph has an inflection point, maybe I'll call it C f of c, then I know something about the second derivative at that inflection point. F prime prime of c is equal to 0, or F prime prime of c does not exist. So basically the same criteria for critical points. I can say that if I want to find possible locations where the concavity of a particular graph changes, then I'm going to look for locations where the second derivative is equal to 0, or the second derivative does not exist. And I'm going to check to see if these are inflection points. So really inflection points are more similar to maxes and mins in the way that we check them than they are to critical points. But we find them in the way that we find critical points. Okay, maybe let's do one example. Let's do this example. Let's let f of x equal e to the x times x minus 3. And let's determine intervals where f is concave up and concave down. Determine the intervals where the function f is CCU for concave up or CCD for concave down. Also, I want to identify any inflection points. Identify any inflection points. Inflection points. That's our goal. To find places where a graph is concave up, concave down, I need the second derivative, because that is what tells me about the shape of a graph. I need f prime prime of x. So let's do that. Let's find f prime prime of x. F prime is what we need first, because I need that to find the second derivative. F prime is equal to, well, let's see. I have two functions. I'm going to write this function out here. F prime of x is equal to e to the x times x minus 3. I need product rule to find the derivative of this. I have one function multiplied by another function here. So I need their derivatives. D dx of e to the x is equal to e to the x. And d dx of x minus 3 is equal to the derivative of x, which is 1, minus the derivative of 1, which is 0. Okay, so I'm going to put those together using the product rule. F prime of x is equal to the first function, e to the x times the derivative of the second function, which is 1, plus the second function, which is x minus 3, times the derivative of the second function, or the first function, excuse me, which is e to the x. I'm going to rewrite this to make it look a little cleaner. This is e to the x plus x e to the x minus 3e to the x. I have terms that I can combine here. E to the x minus 3e to the x is negative 2e to the x. Negative 2e to the x plus x e to the x. And then I could rewrite it in a form that's very similar to what I have above. Factor out the e to the x, and then I have negative 2 plus x or x minus 2, if you prefer. So that is my first derivative. So I've got that. Now I am going to apply those same derivative rules and find the second derivative. F prime of x is equal to e to the x times x minus 2. Idea as before. I have two functions that are multiplied together, so I'm going to use a product rule to find the derivatives. I know that the derivative of e to the x, d dx of e to the x is e to the x. Derivative of that second portion, d dx of x minus 2 is equal to 1. So since I have the functions and the derivatives, I can put them together using the product rule. F prime prime of x is equal to the first function, e to the x times the derivative of the second function, which is 1, plus the second function, x minus 2 times the derivative of the first function, which is e to the x. Going to simplify again, and by the same process we did before, the simplification will be e to the x times x minus 1. So there's my second derivative. First thing I want to do is figure out, well, if the concavity is going to change, it'll happen at locations where this first derivative or the second derivative is equal to 0 or doesn't exist. If the concavity changes, I know this occurs. This occurs where the first derivative, or the second derivative, excuse me, f prime prime of x is equal to 0, or f prime prime of x does not exist. So let's find those locations. I'm going to figure out where is the derivative, f prime prime of x equal to 0. So that is where e to the x times x minus 1 is equal to 0. This part can never equal 0. So I'm not going to worry about that part. But this part can. If I set it equal to 0, then I get that x equals 1. Is one possible location where the concavity changes. I should probably make myself a note, places where that second derivative does not exist. F prime prime of x is equal to e to the x times x minus 1. E to the x is continuous everywhere, x minus 1 is continuous everywhere, so this entire function exists everywhere. So there are no locations where the second derivative does not exist. So I've got those. Now I'm going to do a process very similar to what I did before. I'm going to put that possible location for change, or excuse me, on a number line. And I'm going to test values. I'm going to test, say, 0 and 2 in the second derivative. So f prime prime of 0 is equal to e to the 0 times 0 minus 1, which is equal to negative 1. So the graph is negative, or the second derivative, f prime prime, is negative here. Second, f prime prime of 2 is equal to e squared times 2 minus 1, which is certainly positive, because e squared is positive, 2 minus 1 is positive. So the second derivative is positive in this interval. Well, what's that mean? Since I'm testing in the second derivative, it means the graph is concave down in this interval, and it is concave up in this interval. This is the interval from negative infinity to 1. This is the interval from 1 to infinity. All right. So it appears that this point here is indeed an inflection point. This is a point of inflection. This is the location where the graph changes from concave down here to concave up here. The graph is concave down here and concave up here. And that is how we would find those. I think we'll stop and move on to another video.